try to find what's called a line of best fit. Now, the line of best fit goes to point number 2, the specific model. We've agreed, the general overview says it looks like a line. What line? What line fits that data well? What do you think? Give me some ideas. Who wants to draw one? Nobody wants to draw one. Please? Ashley, excellent. What color would you live in? Green, blue, red, orange, black, purple?
Blue matches the blue dots.
Well, there we go. Excellent. Yes, let's see a line. Yes. Uh-huh. Uh-huh.
Well, that's not very straight.
That's okay. I didn't bring a straight edge either, unfortunately, today. Straight-ish. Good. I like it. We're going to take a fork out of there. I love it. Thank you.
Yeah.
Hey, little Belle. Very nice. What do we think? Curtsy. What do we think? Good, yes? Yes? Ashley, why that one? Just get out of curiosity.
It hits the first, it intersects with the first and the last point.
Very good. How many of you thought the same thing? If we catch the first and last, excellent. Excellent. So many of you would have thought and I've got a feeling you probably learned that at some class somewhere. I guess at Math 60 they probably taught that kind of thing. Perfect. Perfect. No, that's okay.
Oh, no, I didn't think Math 60.
That's okay. Well, at some algebra class, at some point in algebra class, you probably picked first, last points and say connect them, boom. Good. Anybody else want to pick a different one? Actually, before we pick a different one, I want to mention something about what Chrissy said earlier. By hitting the first and last points, there is no what we call error in those points. I mentioned these yesterday, these little distances that miss some of the points. Remember what they're called? That's okay. It's okay if you don't remember. They're called residuals. Residuals, and you don't have to memorize that. You don't. It's not worth memorizing for this course. Well, we'll analyze them in 244. Those residuals represent what's the offness of the model. It's how off the model is from the data. So what do you think you want to make the residuals do in the absolute best fitting model?
All be the same.
All be the same, or at least all be as
Close as possible.
Yes, we want them to be as small as possible. We want the error to be off as much as possible, right? Because if we miss the data, we're missing the reality of what the data is standing for. If we get closer to the data, then we're more closely approximating what the data is telling us. So that's why I love hit, yes, hit, yes. But then I'm like, ooh, off. I wonder if we could do better. Can we draw a better line? I can draw a worse one. I'm going to connect this point to this point. There's a worse one, huh? Because I can make the same claim that Ashley did. Well, I hit 2 points. But then Ashley's going to be like, yeah, but you missed that one and this one, so they didn't see it. So my residuals are terrible compared to Ashley's. But now my next question is, could we make another line that even has smaller residuals than Ashley did? What do you think? Any gut feelings? Ashley says yes, maybe. And I can't do this math in my head. You're about to see why. So I let technology compute it for me. And we're going to analyze this more in 244, the actual ins and outs of the mathematics. I'll show you what the mathematics is actually being done momentarily. But believe it or not, the actual best fitting line, and because I moved the slide, I can't compare it to yours. But remember what Ashley did? She put the first and last points and connected them. The next slide shows us the actual perfect best fitting line. And there it is. Look how close it is to what Ashley drew. It's almost exactly the same line if you think about it. Your line had slope 1.125. How did I know that? Because of magic? No, because you guys calculated it yesterday. Remember? We did that at the very end. You drew the line between the first and the last. So the slope of your line actually was 1.125. The slope of the actual best fitting line is 1.05, off by 0.1%. What's the difference? Only 100,000 people. That's not worth worrying about right now. That's not worth worrying about. I'm not saying people aren't worth worrying about. They are. But I'm not worried about the offness. What I'm stoked about is actually you got so close to the actual model. So that is the actual model. 1.05x plus 33.1. Now, that's the equation, the specific model. We've now arrived at our specific model. Notice how I put at the bottom? X equals years since 90. Y equals millions of uninsured. It's important that your audience knows, if you give them an equation, what your equation means. We know how Americans feel about math. They pretty much hate it, right? And if you just give them an equation, I'll never forget the line in Good Will Hunting when Ben Affleck is talking to Matt Damon. And it's a Harvard bar, they got equations and bleep all over the walls. It's just one of those things. Americans don't like math. I don't know why. It's a beautiful thing, but Americans have this like dislike of math. So help them out. Make sure you tell them what they're looking at. Give them the backstory. But speaking of backstory, where did that come from? Ashley demonstrated where her model came from. She said, I picked the first and the last points, and I drew a line for it. Look at that model. That model doesn't hit anything. It misses all the points, doesn't it? It misses the first one. It's a little bit above the first one. It's a little bit below the last one. But did you catch the residuals? Look how close the residuals are. That's where it wins. It wins because it misses the... Complete that sentence. It misses the... Somebody just said it.
Residual.
No, I'm looking for a descriptive word. So residuals are offness, right?
Misses the point.
Let me ask you a better question. I'm asking the wrong question. So in order for us to find the best fitting line, that's what we're looking for, is the best fit line, the line of best fit. It's also called a least squares regression line. I won't get that right now. It's also called the line that minimizes the residuals. Because if you minimize the residuals, it means you're missing the... You're missing the points how? A lot?
No, by the smallest possible.
By the smallest I was looking for the word least. You're missing the points the least. By the smallest possible amount. That's what I was looking for. It was a tricky question. I should have phrased it better. So what you want to do is you want to describe a line with an equation that misses the points as little as possible. Okay, you ready? Here's how you do it. Exactly. That's what you would have to do.
Oh my god.
Yeah, I know. It's ridiculous.
Is that like calculus?
It is. It's based in... This is actually just pure algebra. But in order to... If anybody wants to see this derived, I didn't believe it when it was given to me in college. So I went home and proved it for myself because I'm that guy. So if you look at the enrichment page on my stat classes, I actually derived these formulas if you're interested. There is calculus involved. As soon as you do something called minimization, it's called optimization in calculus. You want to find either the most or the least efficient way of doing something. You have to use calculus if you're doing it mathematically. You guys remember parabolas?
Yeah.
Remember how parabolas have a high point and they have a low point? Believe it or not, parabolas are behind this. But you can use calculus to analyze them in general because they have that high point. We're actually going to look at the calculus that I'm talking about in this class. Not like that. Oh my God, no. But the basic gist of what's called the slope of a parabola, which sounds like gibberish. How can a parabola have slope? It's not a line. Depends on how you look at it. You can make it have slopes. They have variable slopes. So this, we are not going to do this. We're going to use technology to get that line for us. So what I've done is I've prepared, let's turn this off. I've prepared a little booklet. And I brought one for you because you're 89. That's a special one for the 89.
I'm not quite 89. No, TI 89.
Well, the TI 89 is what I meant. Sorry. I felt 89 this morning. I'll tell you that. I've been out of bed at 4. And I have booklets for the TI 83s and 84s. So grab one, pass them around. If you don't have your machine with you today, that's okay, because you go for somebody else. Grab a booklet though. If you don't have a machine at all, that's okay too. There are other options besides the TI. It just seems like most of you have a TI. So here's a booklet. Spread them around. Work your way through it. That booklet contains the same data set we had up here. And it shows you how to get the exact same result in your machines. Take a few moments right now. As you need, take your 5, because this is going to take us over our break time. So as you need it, take your 5. We'll regroup maybe like 10 after 9 or something and see how we come up with. Cool? All right.